Welcome to qnawire.
Charge density is given by R is equal to 1 minus R divided by R. This is for R less than or equal to R, where rho naught is equal to 3Q divided by pi R3, and rho R is equal to 0 for R greater or equal to capital R. Part A of the problem. The charge density varies with R inside the spherical volume. We divide, so let's say this is a spherical volume here. We divide this into thin concentric shells. So let's say the innermost has got a radius R here, and the distance from here to here, let's represent this from here to here, is del R. R is the radius and dr is the thickness. Dr is a thickness. We find dq in each shell and integrate to find the total charge. So the volume of such a shell will be dV is equal to 4 pi r square dr. The charge contained within the shell will be dq is equal to rho of r dV, which will be equal to 4 pi r square rho naught 1 minus r divided by capital R times dr. The total charge in the charge distribution is obtained by integrating dq over all the shells in which the sphere can be divided. So q is equal to integration of a dq, and we can substitute for a dq from 0 to r. That is a 4 pi r square rho naught 1 minus r divided by capital R times dr. Then we can integrate this to get q to be 4 pi rho naught integration from 0 to r square minus r3 divided by r dr. And this gives us a q to be 4 pi rho naught r cubed divided by 3 minus r4 divided by 4r. This is from 0 to r. Then the final expression that we get here is 4 pi 3q divided by pi r3 times r3 over 12, which is equal to q. Part B, we apply the Gauss's law to spherical surface of a radius r, where r is equal, or sorry, not equal, rather greater than r. This will be, let's say, here we have the outer one, the inner one is here, the radius is r here, capital R, and the radius from inside to outside this Gaussian surface is a small r, and capital Q charge is here. Then we know phi E is equal to charge enclosed divided by epsilon. Then we can write E electric field times 4 pi r square is the flux, that is a Q total charge divided by epsilon, and this gives us the electric field to be E to be Q divided by 4 pi epsilon r square. This is like as a point charge electric field, is point charge electric field. Part C, we apply the Gauss's law to the spherical surface of a radius r. So where r is less than r. So here is the small r, and here is the capital R from here to here. We use the same formula for the flux. Electric flux is given by charge enclosed divided by epsilon, and substituting the flux we can write here is flux is equal to electric field times the surface area, which is 4 pi r square. Then we calculate the charge enclosed and use the same technique as we used in part A, except to integrate dq without the r rather than r. So q enclosed will be integration from 0 to r 4 pi r dash square rho 1 minus r dash divided by r times dr dash. This gives us 4 pi rho naught integration from 0 to small r here. This r dash square minus r dash 3 divided by r dash here. Then a charge enclosed we get here after integrating. We get the charge enclosed to be 4 pi rho naught into r3 divided by 3 minus r4 divided by 4r, and this is equal to 4 pi rho naught r3, taking r3 outside, 1 over 3 we get minus r divided by 4r. Then rho, we can write rho is a 3q divided by pi r3. So charge enclosed will be q r3 over r capital R3 times 4 minus 3r divided by capital R. From the Gauss's law, that is E times 4 pi r square is equal to q over epsilon r over capital R whole 3 times 4 minus 3r over capital R. Then further simplifying and solving for E, we get electric field to be, electric field is a capital Q times R divided by 4 pi epsilon R cube times 4 minus 3r divided by r, where r is less than or equal to capital R here. Part D of the problem, we here plot part D, plot E versus R. So here is the E on vertical axis, and in horizontal axis we have R. So the electric field here increases, reaches the maximum, and then decreases and reaches up to a 2r here. So the point here down here is a 2r, and it reaches a peak at 2r over 3, and here is the r where it goes down. The peak we have here is q divided by 3 pi epsilon r square, and here we have is q divided by 4 pi epsilon r square. Part E of the problem, where the electric field is a maximum, dE divided by dr is 0. Thus we can write electric field d divided by dr of 4r minus 3r squared divided by capital R from the above equation is equal to 0. From here, solving for r, 4 minus 6r divided by r is equal to 0. So r will be equal to 2r divided by 3. And the electric field for the value of r will be E will be equal to q divided by 4 pi epsilon r cubed 2r divided by 3 into 4 minus 3 over r 2r divided by 3 is equal to q divided by 3 pi epsilon r squared.